Okay, this is week 9, induction, part C, eddy currents. So let's imagine that you have a region with a B field in it. So let's imagine some region, a kind of a squarish region, like so, maybe a little wider. And there's a B field going into the board in just this region. Outside of it, the B field's 0, and then suddenly you've got a strong B field, some kind of a big magnet right here, north end, with the end pointing into the board, and behind the board is the south end, so that just in this little region, you've got a strong magnetic field. And then you come along with a square loop of wire. And this loop of wire is going to move through this region. We want to see what's going to happen while it does that. So let's have this moving along with some velocity. While it's sitting out here, of course, there's no B field, there's nothing going to happen. But as it goes into this region, there's going to be a changing flux through the loop. As it enters this region, flux is going to increase, and as it leaves the region, flux is going to decrease. So there's going to be a changing flux that's going to induce a current in this loop of some kind. And that current, some of it, will be passing through a magnetic field, and there will be a force on the wire. So let's take a look at this one step at a time. While it's out here, there's no B field ever. There's no changing B field. There's no current. There's nothing happening. Now let's imagine that the loop is in this position right here. While it's in that position and it's moving to the right, there's a certain amount of flux. Now remember what flux is. The flux is the integral over the surface of B perpendicular dA. So what you've got to do is imagine over this surface how much area is there a B field in it. If you look at it, this region is covered by a magnetic field. This is not. There's no magnetic field here. There is there. So in this region, we're going to get a perpendicular magnetic field over that area. And so this is basically going to be the B field times the area, ultimately, except that it'll be a restricted area. It won't be the whole surface. It'll just be that region right there. The rest of it doesn't have any. So you're going to get something. It's going to be that B field times whatever that area, but it grows. As this thing enters that region, the flux is going to grow. So it's a B field times an area that keeps growing. So the flux is increasing. And if you recall, there's an EMF generated that is according to how the flux changes. And that minus sign reminds us of Lenz's law that says current would tend to go around this loop in whichever direction is necessary to oppose the change in the magnetic field going through the loop. So here what we've got is more and more flux going through the loop this direction. So current will go around this loop in such a way as to oppose that, so that the field generated by that current opposes the field that's already, well, the field that is changing. Let me say that again. The change in the flux is what's being opposed. So if there were flux lines going through here and we're getting to have more of them, then the current will go in the wire in such a direction as to oppose that increase. So if we're getting more of them going into the board, which way around does the current go to oppose that? Remember, you grab the wire with your thumb in the direction of the current, your fingers point in the direction of the field, and here we have to figure out, well, which way should the field be? You're getting more and more into the board, so you need some coming the other way to oppose that change. So you got to have fingers coming out of the board, and so your thumb is going to be going around this way. So we expect current, at this case, to be going that direction around the loop, while it's entering. Now we've got current going around the loop. What's the force on the wire? We're going to do this in sections. So we'll take each section of the wire. Out here, of course, the current flowing along that piece of the wire isn't in any magnetic field, so there's going to be no current, no force on the wire up there. But down here, part of that current is flowing in a region where there is a magnetic field. So right along there, what's the direction of the force? You remember how we get the magnetic force on a wire? The magnetic force is I/L cross B. So you point your fingers in the direction of the current, and then turn your hand so you can curl your fingers in the direction of the B field, and your thumb of your right hand is in the direction of the force. So start with your fingers pointing in the direction of the current there, something like this. And then can you curl your fingers in the direction of the field? You can, just like that. So the force will be up. Now see if you can get the force on that piece and on that piece. Try that yourself. Point your fingers in the direction of the current, curl your fingers in the direction of the B field, and your thumb gives you the direction of the force. Got it? So you should have along here, current this way, field that way, force over this direction. Along the top, current this way, field that way, so the force is down. There's no force out here and no force over there. So the top and bottom are going to cancel each other, but from the right side, there's a force against the direction this thing is moving. It's moving along at some speed, it's going to have a force against it. And it's a little hard to see right here, but that force depends on the speed. Talk about that a little more in a minute. So this force will be present as long as this is growing. Then once it reaches full size, so that all of the loop is inside this region, then there's no longer any force, because the current stops. There's no changing. You have flux, but the flux isn't changing, so there's no induced EMF, so there's no current flowing and no force acting on that current. Now let's look at what happens when it leaves. As this leaves, now you again have a changing flux. There's flux going through here. Now you've got a different region. Here's the region where there's a magnetic field. So the flux would be whatever that magnetic field is times that much area, which is shrinking. As the loop leaves the region of the magnetic field, that area shrinks. So you're getting less and less flux through the loop, and that reduction in flux causes an EMF, an induced EMF, which makes current flow. Which way does current flow? Now remember, current flows in such a way as to oppose the change. So now you've got flux going this way, but it's disappearing. It's going away. And so the current flows in such a way as to replace what is going away. And so current will flow so that my fingers go the same direction. You end up with current going this way around the loop. That's the opposite to what we had here. Now, see if you can work out the forces. What will be the forces on those little segments of wire this time? See if you can do them all. Point your finger in the direction of the current. Say we start with this bottom segment right down here. You've got current flowing that way. You've got a B field going into the board. What's the direction of the force? Got it? Current that way. Field is into the board. I've got to turn my hand around, and I got a force going down. What about this section? Current's going up. Field is into the board. Current is up. into the board, so I get a force going this way. And you can probably guess the force in this part is up. Once the loop leaves the area entirely out here, then there's no force anymore. No current flows, there's no change in flux, so no induced EMF, no current flows, nothing happening, no field anywhere. But what's interesting here is both times, do you see the net force here is going to be a force to the left, opposing the direction it's moving. And what about over here? As it leaves, it again gets a kick against the direction that it's moving. So in both cases, there's a push against the way it's moving. That force, it turns out, is proportional to the velocity. If you think about that, the change, the rate of change of the flux would depend on how quickly it moves in here. And the faster it moves in here, the bigger the rate of change, the larger the EMF, the larger the current that flows, and that gives you then a larger force. It's all proportional the whole way. So you get ultimately a force, a retarding force, that's proportional to the velocity. If it's moving really slow, there's hardly any effect. But if it really tries to move fast, it gets a really strong retarding force. This is very useful. And it is used in a bunch of different situations where you want a nice, smooth force that only applies when something is moving. We've seen this actually, most of you saw this last fall. So here's a piece of aluminum and a strong magnet. And aluminum is not magnetic. It's not attracted to the magnet. Nothing special happens here. I don't think I want to stick a piece of steel in here. It would stick very strongly to this magnet. But there's no special effect here until you try to move this thing. And then you get a weird effect. Some of you remember the feeling I'm feeling right now, that this feels like it's stuck in molasses or something like that. I push it back and forth. Now if I drop it, you'll see the effect, I think. It seems not to fall as fast as it should. It's being retarded by this weird force. What's going on there is a little different from this situation, but it's comparable. So here's the large piece of aluminum. And then there's a small region with a strong magnetic field in it. Let's have the field going into the board like that. What you do is you consider different loops, possible loops within the metal of the aluminum. Now, if this aluminum is dropping down, then this particular dotted line, this possible path of current going around within the aluminum, is moving down. It's leaving the field. And so the flux that's going through it that direction is disappearing. So current would go in such a way as to replace it. So you'll have current going around like that. And by a similar analysis, you could figure out that up here you'd have current going the other way around. And so you'd have the current going around like that. And you'll have these are called eddy currents. They go around in these funny little eddies like so. And by a complicated, well, I don't know if it's complicated, by a mechanism that I have not seen described anywhere, the forces that act, like we saw forces on these loops, there are forces acting on these loops of current that push on them, and somehow that force gets transferred to the aluminum itself. It's not exactly clear to me how that happens, but it does. And what you end up with then is a retarding force that's proportional to velocity. And so when I hold the aluminum just steadily, there's no force at all. When I try to move it, I can feel there's a retarding force, and it's a force that's kind of proportional to velocity. If I push hard, I can feel there's a strong force. That's very much like sort of liquid frictional forces. When you put something into a liquid, especially a viscous liquid like honey or molasses, and try to move it, if you try to move really slow, there's not much effect. But when you try to move hard or fast, then you feel that retarding force, that strong retarding force. This is used in other contexts at amusement parks at the end of a roller coaster ride. there are brakes that are designed this way. So in the car that you're riding along in, there's a fin, aluminum fin, that sticks down between some magnets that are in the track. And that way, if you're coming to the very end of the track, you still have to have some velocity to sort of get you there, but it may be faster or slower, and they use these brakes to slow you down very smoothly. And if you're really moving fast, the brakes apply a really strong force to slow you down. If you're not moving very fast, then they sort of let you go on through. It's just exactly the right thing you want, and it doesn't depend on electricity. So this can also be used in drop tower. This ride where you sit on these seats and they pull you up to some tall tower and then let you drop. And you'd like to think that whatever brakes are going to slow you at the end of that are going to work no matter what, even if there's a power failure at that moment. And this is the way it is done, in fact. If you look on the tower, you can see fins, and there are magnets on the car that go across those fins. Slow you down no matter what. I'm going to demonstrate this one more way. Got to take and move you just a little bit so that you can see what's going on. So what we're going to do, I have here an aluminum tube. It's just a plain tube. There's nothing special about it. And here is this really strong magnet that I had before. And if I hold this under the mirror, you can see right through it. And I can drop this through, and you can see the whole process. See how it goes down very, very slowly. That again is inducing currents in this aluminum cylinder. And those currents delay the whole thing. They retard its motion.